Okay, let's dive right into this. Today we're exploring a literal Cinderella story of scientific redemption. You see, for centuries, the silk industry has been completely obsessed with just one thing, producing those beautiful, shimmering threads that make up luxury fabrics. But in the process of harvesting all that pristine silk, something else was getting left behind. It was being washed right down the drain. Literally. We're going to explore the absolutely fascinating transformation of silk's discarded glue, a little protein called sericin.
I mean, it sounds like the setup to a sci-fi movie, right? What if the silk industry's absolute biggest waste product turned out to be a medical marvel? For decades, silk producers were throwing away thousands of tons of this byproduct. They considered it nothing more than a sticky, gooey nuisance. But recently, science took a much closer look at what was being tossed out with the bathwater, and wow, what they found is completely upending our entire understanding of biomaterials.
Section 1. Silk's Misunderstood Glue.
So, to really get this, we have to look at the two main players. First, you've got fibroin. This is the superstar. It makes up about 70 to 75% of the silk protein. It's that fibrous, super strong, beautiful thread used in high-end textiles and, more recently, even advanced biomedicine. But then, we have sericin. Sericin makes up the remaining 25 to 30% of the silk. When a silkworm spins its cocoon, it secretes two strands of fibroin, and then it coats them in sericin, basically a sticky glue that holds the entire cocoon structure together. For a really long time, reelers and silk processors just wanted the fibroin. The sericin was just this annoying gum getting in the way, so they would literally boil it off and chuck it away as waste.
And here's the crazy part. It wasn't just that sericin was viewed as useless. It was actually considered dangerous. There was this highly cited biomedical study published back in 2003, and they stated, flat out, that sericin, glue-like proteins were the major cause of adverse problems with biocompatibility and hypersensitivity to silk. Basically, the scientific consensus was that if you put sericin anywhere near the human body, it would trigger a massive immune response. The medical community slapped a toxic hazard label on our misunderstood hero, and sericin was totally blacklisted.
Section 2. Anatomy of a protein.
But then came the plot twist, and the scientific gold rush that followed was just massive. Back in the year 2000, research publications on sericin were practically non-existent. But as researchers started to actually test sericin independently of the harsh chemicals that were traditionally used to extract it, they had a huge realization. Their assumptions about its toxicity were dead wrong. The real culprit behind all those allergic reactions? It wasn't the sericin at all. It was the degraded, chemically treated mess left over from the traditional silk processing. Once they realized pure sericin was actually safe, research absolutely exploded. It jumped to over 250 papers a year in 2012 and then skyrocketed to nearly 600 publications a year by 2023.
So, where exactly does this magical glue even come from? Deep inside the Bombyx mori silkworm, there's a specialized area called the middle silk gland, or MSG. As the silkworm gets ready to spin its cocoon, this highly specific region synthesizes and secretes 3 different types of sericin. It's basically a highly specialized, tiny biological factory totally dedicated to producing this exact protein.
Okay, but chemically speaking, what actually is it? Well, sericin is a globular protein. When it's sitting inside the silkworm's gland, it's soluble in water and exists in this loose state of random molecular coils. But the moment it gets spun out and hits the air, it dynamically changes its structural shape. As it dries, those random loose coils instantly convert into rigid structures known as beta sheets. This phase change is literally what turns a liquid secretion into a rigid, waterproof adhesive designed to protect the developing moth inside the cocoon. It's a highly responsive material, reacting super intensely to any changes in temperature and moisture.
Section 3. The Extraction Dilemma.
Now, here's the central problem. Getting that sericin off the fibroin thread without completely destroying it is incredibly tricky. The conventional method, the one used for centuries, involves boiling the silk in harsh soaps and alkalis. And yeah, this works great for getting pure silk thread, but it highly degrades the sericin, chopping its molecules to pieces and creating a ton of toxic wastewater in the process. Then you have the thermal method, which is essentially pressure cooking the silk in an autoclave. This is simpler and doesn't leave toxic residue, but high heat still degrades the protein somewhat. Finally, we have modern methods like infrared heating and microwaves. These are eco-friendly, and they use electromagnetic waves to gently detach the sericin, beautifully preserving its molecular structure. The catch? They require highly specialized and incredibly expensive equipment.
Section 4. Refining the silk protein.
Let's cleanly map out the journey of turning this raw glue into a usable biomaterial. It's a precise 4-step scientific rescue mission. Step 1 is degumming, where we separate the glue from the thread using one of those methods we just talked about. Step 2 is precipitation. Here, scientists add salts or use freezing to force the Sericin to separate right out of the liquid solution. Step 3 is dialysis. Think of this as a really deep clean that purifies the solution by removing any residual chemicals or salts. And finally, step 4 is drying. By using advanced techniques like lyophilization, which is basically freeze drying, all the liquid is removed. This leaves behind a highly stable, completely pure Sericin powder that is totally ready for medical use.
Section 5. The future of biomaterials.
Because once we get that pure powder, it turns out Sericin has an absolute arsenal of superpowers. First and foremost, it is highly biocompatible. Remember that 2003 study we mentioned earlier? Completely debunked for pure Sericin. It causes almost zero immune rejection. It's also biodegradable, meaning our bodies can naturally break it down over time safely. But here is where it gets absolutely crazy. Thanks to its unique amino acid profile, specifically its high cysteine content, pure Sericin is inherently antibacterial. It literally disrupts the metabolic processes of microbes. Plus, its high levels of serine and threonine make it incredibly efficient at scavenging reactive oxygen species. That makes it a powerhouse antioxidant, giving it massive anti-aging and UV protective properties. No way, right?
All of this leads us to the incredible real-world applications we're seeing today. The transformation here is just stunning. We start with a raw, crawling Bombyx mori silkworm, and we end up with a highly refined, purified powder. This very powder is now being engineered into hydrogels for advanced wound healing, into scaffolds for growing actual new human tissue, and even into sophisticated drug delivery systems that can carry medicine directly to a target inside the body. And because of those anti-aging and UV properties we talked about, it's also absolutely exploding in the cosmetics industry, finding its way into high-end moisturizers and skin creams. We are talking about a stunning transformation from a discarded bug byproduct into a highly valuable medical and cosmetic powder.
So you see, Sericin truly is the Cinderella story of biomaterials. It went straight from the drainpipe to the absolute cutting edge of modern medicine. And it really makes you wonder, doesn't it? As our extraction technologies get better and our understanding of biology deepens, what other quote-unquote waste products in our world might be hiding secret superpowers? I mean, if we can find this much value in the discarded glue of a silkworm cocoon, what else are we totally overlooking? I'm going to leave you with that thought. Thanks for joining me on this explainer, and definitely keep your eyes open, because the next medical marvel might just be hiding in the trash.